Now that we are able to design an analog filter, we have to learn how to convert this analog filter into a digital filter. There is a need for a transformation which produces a stable filter in the analog domain. Then the transformation should yield a stable filter in the digital domain as well. We need to transform the system function h of z in the S domain to h of z in the z domain. H of z is the analog domain and h of z will be the digital domain. The frequency, analog frequency indicated as omega, will be transformed to the digital frequency which is called as omega. Now here we talk about a method which is called as bilinear transformation. This method is used to transform the analog filter to a digital filter. Let us arrive at the relationship for bilinear transformation. The area under the curve can be determined using the normal integration. Y of t is equal to integral 0 to t x of t dt. This expression provides you with the area under the curve, which is y of t. X of t is called as the curve function and t is the upper limit of integration. This integration equation could be converted to differentiation if you take derivative on both sides. It becomes d by dt of y of t is equal to x of t. This can be expressed as a Laplace transform as taking Laplace transform on both sides, s times y of s is equal to x of s. Alternatively, for the integral equation also we can provide the Laplace transform as y of s is equal to 1 by s times x of s. Now, the area can also be determined using a different method. The method that we use now is called as digital integration method to compute the area under the curve. In this method, we can observe that the curve here is x of t, it's a function of time. We can find the amplitudes at different instants of time. For example, let us consider the instant which is n times of capital T. The amplitude at that time n times nt is denoted as x of nt, which could be approximately written as x of n. Similarly, the amplitude at the instant n minus 1 times t is x of n minus t, which could also be expressed as x of n minus 1. Now, we can compute the area of the curve at different instants of time. If you include the instant up to n minus 1 times of t, the area is said to be equal to y of nt minus t, or alternatively it is y of n minus 1. If we include the additional time period which is equal to capital T also, then the area now becomes y of nt, which is equal to y of n. Therefore, if using the numerical integration method which is shown in the figure, this area can be indicated approximately as y of n equals y of n minus 1 plus x of n plus x of n minus 1 divided by 2 times t. The method is very simple. First, we compute the area up to the time instant which is n minus 1t. It is given by y of n minus 1. The extra area which is obtained after the additional time interval of t is calculated as follows. We know the width is equal to capital T. The height is determined using the average amplitude. To calculate the average, we take x of n plus x of n minus 1 divided by 2. So we are getting the average height multiplied by the width. This is equal to area. Hence, equation 3 tells about the total area under that curve. Now, from the previous application of Laplace transform, we have seen that the Laplace transform of equation 1 is y of s is equal to 1 by s times x of s. If we convert it to a transfer function, then h of s is equal to the ratio of y of s by x of s, which is equal to 1 by s. This is called as the transfer function or system function in S domain. Now, we have computed the various values. Now, let us apply the Z transform for this. Since it's in a digital domain, we have to take Z transform. Now, applying the Z transform on both sides of the equation will give you the result y of z is equal to z power of minus 1 y of z plus t by 2 times x of z plus z power of minus 1 x of z. And we have to solve for the ratio, that is y of z by x of z. The simplification may be done as shown here. So first we gather the y of z terms together, and on the RHS we collect the terms with x of z together. Then we take the ratio of y of z by x of z and take all the other terms to the RHS. And hence we obtain the result t by 2 times 1 plus z power of minus 1 divided by 1 minus z power of minus 1. So this equation 4 is providing you with the transfer function in the digital domain. Now we can observe that we have h of s as given here, and we have h of z as provided there. Now if you compare the right hand side of the two equations, it gives you a relationship between s and z. Therefore, we can express it as 1 by s is equal to t by 2 times 1 plus z inverse divided by 1 minus z inverse. Or alternatively, in terms of positive powers, we can also write it as t by 2 times z plus 1 divided by z minus 1. Solving for s, we get the equation as s is equal to t by 2 by t times z minus 1 by z plus 1, or in terms of negative powers, the value is 2 by t times 1 minus z inverse by 1 plus z inverse. This particular relationship is called as the bilinear transformation. This bilinear transformation helps us to replace the value of s in the transfer function h of s and convert it to the transfer function in the digital domain, which is called as h of z. Alternatively, we can have the reverse transformation also. So if you rearrange the terms and get the equation for z, the equation is going to be 1 plus t by 2 times s divided by 1 minus t by 2 times s. Now, let us summarize some aspects about this particular mapping. The properties of the mapping are summarized as follows. Number 1, the left half S-plane is mapped onto the inside of the unit circle of the Z-plane. The right half S-plane is mapped into the outside of the unit circle of the Z-plane. The positive j omega portion in the S-plane is mapped onto the positive half circle on the unit circle, while the negative j omega axis is mapped onto the negative half circle on the unit circle. These 3 points can be viewed from the mapping shown here. The one on the left is the S-plane, the one on the right is the Z-plane. We can see the S-plane real part is sigma, imaginary is indicated as j omega, and here we have real part of z and imaginary part of z. Now, in the z plane, we have the circle which is called as unit circle. The region inside the unit circle is called as a stable region. Whereas for the S plane, the region on the left of the imaginary axis is called as a stable region. Now, the point number 1 mentions that the region on the left maps to inside the unit circle. According to point number 2, the region which is the unstable region that lies on the right side of the j omega axis maps to the exterior of the unit circle. So what is unstable in the S domain will be unstable in the Z domain as well. Coming to the third point, the region in the positive side of j omega, which lies on the j omega axis, the positive will be on the upper half of the circle, whereas the region which is negative j omega in the S plane will lie in the lower half. So we understand that the mapping in the S plane to Z plane will provide you with a stable filter. Next we discuss about the concept which is called as the frequency warping. A frequency indicated as omega A, if it's an analog frequency, and omega D is a digital frequency. The analog frequency is measured in terms of radians per second. The digital frequency should be measured in terms of radians. It's just radians in terms of units. Now, the mapping between the two frequencies is shown in the diagram. So we observe that a frequency omega A, which is an analog frequency, maps on to a digital frequency omega D. If it lies on the j omega axis, it lies on the unit circle in this case. On the unit circle, we know the magnitude of Z is going to be equal to 1, and the angle is given by what is called as omega D. Now, to understand the implication of this, we substitute the value of S is equal to j omega. So since you are dealing with the analog frequency, you may call it as omega A. And Z is equal to e power of j omega dt. If we insert these relationships into the bilinear transformation, what will happen? So first we are substituting for S value, which is j omega A, and then we have 2 by t times e power of j omega dt minus 1 by e power of j omega dt plus 1. Simplifying this equation as shown, we can take e power of j omega dt by 2 common, and what remains is we get 2 by t sine omega dt by 2 cos omega dt by 2. That is 2 by t times tan omega dt by 2. Now this equation provides you with a relation which exists between the analog frequency and the digital frequency. The equation above states the relation between analog frequency on the j omega axis and the corresponding digital frequency omega d, which lies on the unit circle. The inverse of this, the inverse relationship, is given by omega d is equal to 2 by t tan inverse of omega a times t divided by 2. The range of digital frequency omega d is said to lie from 0 to omega s divided by 2, which is referred to as the folding frequency. Here's a plot of the relationship between omega a and omega s. So what we observe here in the diagram is that up to a certain point the relationship between the two is almost linear, but you have a region between 0.32 omega s to omega s which shows a bending. It is non-linear. So this non-linearity in the relationship between omega a and omega d is termed as frequency warping. Warping is nothing but a distortion or bending which is exhibited in the relationship. Ideally, we wanted the relationship to be linear, but here it is not linear. It has a non-linear section. To overcome this particular problem, we can go with the method which is called as pre-warping. So in the bilinear transformation method, the steps will be as follows. First, you'll be given the problem digital specifications. The digital specifications are Kp, Ks, omega p, omega s. Then we go for a step called as pre-warping. So after pre-warping, we obtain the analog specs as Kp, Ks, omega P, omega S, and later we do what is called as n-log design. At the end of n-log design, we get the transfer function HA of S. Then we apply the bilinear transformation method and convert it to a digital filter with the transfer function H of Z. This will complete the design. The same concepts are illustrated here as shown in the diagram. So the steps are as follows. So to avoid the frequency warping, in step 1, we are collecting the digital specifications. We are transforming it to analog specifications. We perform a step which is called as frequency pre-warping. So to avoid the nonlinearity, we pre-warp the frequency and then we perform the steps so that the problem of the nonlinearity is solved. Frequency pre-warping is described as omega A is equal to 2 by T times tan of omega dt divided by 2. So this way we can convert it into an analog frequency and then we can perform what is called as the analog low pass filter design using the specification. And after that step, in step 2 we have the analog design, and then after that in step 3 we go for the digital filter by applying what is called as bilinear transformation method. Thank you all.